This is Chapter 17, Part B. This is sort of connected to Chapter 17, that's related to the notions of irreducibility and reducibility, but I'm going to put it separately because I think it sort of deserves its own section. So this is basically just a couple of connections that arise between quotient rings and, let's say, irreducibility / reducibility. So there are two sort of interesting things I want to sort of introduce here. So they're both theorems, both fairly straightforward to prove, although there are a few things we'll need to remember from earlier in the course to do them, but they're not difficult, but there may be a couple points where I pause to remind you of some things. So the first one is to let F be a field and P of X be in F adjoint X. So then it turns out that the ideal generated by P of X is maximal if and only if P of X is irreducible over F. So you may need to look up again what an ideal generated by an element is, a principal ideal generated by P of X, and you may need to sort of recheck what maximal is. I'll discuss them briefly as we use them, but I won't go over the definitions again. So what I'll do is I'll prove this, and then I'll give an example of why this is useful. So it's an if and only if, so we have two directions. So for the forward direction, we'll suppose the ideal generated by P of X is maximal. And we're going to claim that P of X is irreducible over F. So a couple things to mention about P of X. Right? So note, P of X is not the zero polynomial, because the ideal generated by the zero polynomial is just the zero ideal, which is not maximal. So I'll leave it to you to ponder why not. Sort of an interesting little fact on its own, but think about it. And P of X is not a unit because the ideal generated by a unit is everything. So this is something that's come up before. So think about that if it's not clear. And that's not maximal. That's a lot obvious. It's a lot more obvious. It's because a maximal ideal has to be a proper ideal, and the entire ring would not be a proper ideal because it's not a proper subset. Right. So now we're claiming that P of X is irreducible. So let's put P of X equal to G of X, H of X. And what I'm going to claim is that one of those two is a unit, right? Now, to claim that one of those two is a unit means that the degree of one of them is 0, and the degree of the other one is the same as the degree of P of X, right? So the goal is to show that one of them has degree 0 and the other one has the same degree as the degree of P. Or either of those two, because they're equivalent. So knowing that one of them has degree 0 means it's a constant. A constant in a field is just a unit, right? Because a constant in Fx would just be an element of F, right? So now having P of X equal to G of X, H of X, if you look at the ideal generated by P, actually let's do this in steps, right? So then P of X itself is in the ideal generated by G of X, because it's G of X times something. So then the ideal generated by P of X is contained in the ideal generated by G of X, which it itself is contained in the entire ring, F of X. Now, the ideal generated by P of X is maximal. That's the hypothesis. So this means this ideal in the middle, G of X, is either the ideal generated by P of X or the ideal generated by G of X is everything. This is what it means to be maximal. Remember, it means if something is between u and everything, then that something is either u or it's everything. So look at these two cases. And so if we have the first case, so this is where you need to look back at an earlier theorem. We had a theorem that said when you have f of x, f adjoint x for f of field, that if an ideal is generated by a single element, that then it's generated by an element of minimal degree. So this means G and P both have minimal degree within the ideal. They're the same ideal now, right? So what that tells us is that the degree of G is the degree of P. This is because both have minimal degree in the ideal. This is by a previous theorem. So the fact that they both have the same degree gives us our fact, right? In other words, if the degree of G is the same as the degree of P, we can say that the degree of h of x must be 0, right? We're referring back here to this fact in blue that I'm circling here. So the fact in blue says, well, if the degree of G is the same as the degree of P, then the degree of h must be 0, because the degrees add. So that says that h of x is a unit. And that's what we wanted, right? Now, this is only in the case here, just to be clear, we're done one case. This is the case if g of x, if the ideal generated by g of x is the ideal generated by p of x. Right? So on the other hand, if the ideal generated by g of x is everything, right, what happens then? Well, everything, the entire ring can be thought of as the ideal generated by 1. Right? So what this means similarly is that the degree of g of x must also be 0. So then g of x itself is a unit. And back to that fact in blue, since g of x is a unit, we've now proved irreducibility. Thus p of x is irreducible over f. So that's the forward direction. Backward direction a little quicker. All right, so for the backwards direction, we're going to suppose that p of x is irreducible over f, and we're going to claim the ideal generated by p of x is maximal. So to do this, let's suppose that p of x is contained in an ideal I, which is contained in everything, and we claim that I is one of those. Right? Now, we had another theorem that said f adjoint x is a PID, is a principal ideal domain. Right? So what that means is every ideal, I, for example, is generated by something. Right? So since f adjoint x is a PID, this is again as a previous theorem, we know that I is generated by something, some g of x. It just says for g of x, but really for some g of x. So now, really we have p of x, the ideal generated by p of x is contained in the ideal generated by g of x, which is contained in f of x. So this tells us that p of x itself is an element of the ideal generated by g of x. So what that says is that p of x is g of x times h of x for some h of x in the big field, or in the big f adjoint x. But now, of course, we know that p of x is irreducible. So what does that tell us? So that tells us that either G or H is a unit. So now if G of X is a unit, then I, which is generated by G of X, is everything. And if H of X is a unit, then I, which is generated by G of X. So now what we need to do is we need to refer back very, very briefly, we use a different color, to this factor right here in pink, circle in pink. So when we refer to that, back to that, the ideal generated by G, if H of X is a unit, then the ideal generated by G is exactly the same as the ideal generated by P. So that might take a few minutes of thinking about why that is, that if you generate something by G, and then you take G and you multiply by a unit, and you generate something by that thing, it doesn't change. So either which way, we have our conclusion, because now here I is P of X. So remember to prove that, remember, don't lose track of where we're going here. To prove that this ideal is maximal, we made this supposition right here. I'm circling in green, and we're showing that I is either the ideal generated by P of X, or it's the ideal generated, or it's the entire F of X. And so that's what we've proved. So now we're at QED. So what I want to do is sort of show you why this is the case, or why this is useful rather. And to do that, I want to couple it with a previous theorem. So what I'm going to do is I'm going to clear the screen, and I'm going to sort of make a note, mention the previous theorem, how it couples with this, and then I can sort of show you an example of why this is kind of cool. So here's a note I want to make. So let me sort of explain why this is useful. So this can be used to help construct field. So for example, I'm going to give you an example that doesn't use this, and then I'll give you an example which does, and I'll refer to this theorem again and the theorem that goes with it. So suppose you want a field, let's say suppose we want a field with, say, 7 elements in it. This is easy. We just use Z7. And we're done. All right, now, again, convince yourself if you're not convinced that Z7 is a field. But it is to come up. Things like Z7 when it's prime, Z sub P is a field. But suppose we want a field, say, with 27 elements. So we cannot use Z27. This is not a field. It's not even an integral domain. Right? For example, 3 times 9 is 0, which doesn't happen in a field. Right? So cannot do this. So you might be like, well, how do I do this? Like if I can't use Z27, what do I do? Right? So recall we had a theorem from earlier in the class. Right? It was a theorem just about ideals and rings. So it said an ideal I of R is maximal if and only if R mod I is a field. We proved this way back. This was back in the section on quotient rings. So what this tells us, couple this with the theorem that we just gave. Right? So let's say if big F is a field, right, then what can we say? We can say that P of X in F adjoined X. Right, so F adjoined X itself is not a field, right? Not at all. So this is irreducible if and only if. So the first part is the theorem that we just did. This is if P of X, the ideal generated by P of X rather, is maximal. That's the theorem we just did. Now the theorem that I just listed connects it to saying that F adjoined X mod the ideal generated by P of X is a field. Now, you might be like, well, this just sounds awfully complicated, so how do I actually use it in practice? So, consider earlier in this section, we showed, in other words, this was in part A, so you may want to look back at part A if this doesn't ring a bell. We showed that this polynomial, x cubed plus x squared plus x plus 2, is irreducible over Z3. Now, I'm going to make a few comments here about this. I'm about to construct a field, and I'm going to say something about this field, and you may need to dig into the details to sort of hash this out. So I'm just going to sort of make this overall statement. But we've done all these bits before, or the thing I'm going to mention we've done before. So we showed this was irreducible in Z3, so you can check back to 17A to see how we did that, right? So what does that tell us? Right? It tells us that Z3 adjoined X mod the ideal generated by that element is a field. So then you might say, well, great, what do things look like? What do elements in this look like? So for this, you definitely want to look back at where we looked at quotient rings, because we worked through some examples like this. There was one video on quotient rings where I worked through a couple of these, at least one that sort of really dug into the details of this. But in this case, I'm just going to answer the question. They look like ax squared plus bx plus c plus the ideal generated by x cubed plus x squared plus x plus 2, where a and b and c are in Z3. So, and each are unique, each is unique. So for what it's worth, before I sort of come to the conclusion here, this is not screamingly obvious. I mean, it might be to you, but without sort of digging back into the details, it's not. If it is obvious, it's because you understand the details. But if it's not obvious, it's because you haven't sort of hashed out the details. But then we see each is unique. There are 3 choices for A, 3 choices for B, 3 choices for C. So 27 elements total. So we've got our field, right? So this is sort of an interesting way to construct fields that have desired numbers of elements that you can't do just with like Z sub p. Okay? So last connection to quotient rings I want to give is a little bit quicker. So let me clear the screen. I'll give that, make a couple notes about it, sort of interesting facts, and give a proof which is fairly quick. So this is part 2. It's really a corollary for what we did, but I'll state it as a theorem. So just for reference, in chapter 18, the next chapter, we're going to talk a lot about these things called irreducibles, which kind of will be connected to this, or will seem connected to this theorem we're just making and we're about to give. And so these notions might seem a bit confusing at first, but they're not. But there'll be a parallel there. So this theorem says the following. It says let F be a field. In other words, the theorem that I'm about to give might ring some bells when we get into the next section. And we'll say let P of X, A of X, and B of X be in F adjoined X. So then the deal is this. If P of X is irreducible over F, then if P of X divides A of X, B of X, then P of X divides A of X, or P of X divides B of X. Now before I go any further, I want to make a note. This is especially useful for people who are in number theory, who have seen sort of this concept come up with primes, and it's sort of also a prep for chapter 18. We're going to sort of mix the divisibility up a bit, but it's a property of primes, like prime numbers, literally sort of standard prime numbers in number theory, that if P divides A, B, then P divides A, or P divides B. So in fact, in chapter 18, we're going to define a prime. Specifically, we're going to sort of turn things on their head a bit. We're going to define a prime as being something, a number that satisfies if P divides A, B, then P divides A, or P divides B. And then we're going to have a different notion of irreducible. But in this case, like in this particular theorem, what we're saying is like that when you have this irreducibility fact, that you get this property that we think of as a property that prime numbers have, right? That when you divide a product, you must divide one of them. So the proof of this is fairly straightforward. We'll say, since P of X is irreducible over F, we know that F adjoint X mod the ideal generated by P of X is a field. That's literally just the theorem that we just did. Now, fields are integral domains. In other words, F X mod the ideal generated by P of X is an integral domain. Now, we had another theorem earlier in the course that said that R mod I is an integral domain if and only if I is a prime ideal. Thus, this is a prime ideal. Now, what does it mean to have a prime ideal? It means if you have a product in the ideal, that one of the two things must be in the ideal, right? So now, the fact that P of X divides A of X, B of X, this implies that A of X, B of X is in the ideal generated by P of X. So then, either A of X is in the ideal, this is the definition of a prime ideal, or B of X is in there. So in the first case, if A of X is in the ideal generated by P of X, that means P of X divides A of X. And in the second case, that means P of X divides B of X. And that's the end. So I'm not going to do any examples of this. There aren't really any examples to have, but it's sort of a fun fact. It's interesting because it sort of gets you ready for chapter 18, which could be a bit confusing because we're going to bring the word irreducible up again in a slightly different context. We're going to sort of redefine the term prime. We're going to hash that all out. But this is sort of giving an example of where like those concepts, the concept of irreducibility and the concept of prime from number theory, this concept right here, for those of you that are in 406, this is pretty familiar, that those sort of two concepts are tied together in certain ways. So that's the end of this chapter completely.